to a closed contour integral. So we've got a surface integral, we've got a surface element of integration, and the argument is going to be curl E, and it takes us to a closed contour integral. The element of integration on the path is a path element ds, and we project the electric field onto each path element. It's going to be the unit normal S of that path element. And here, if we complete the fact that we've transformed curl E into a surface integral, likewise we've got minus 1 on C. We've got two operators. There's a time operator and then a space operator. They can be separated, and here we've got a surface integral, and the integrand is the projection of the magnetic field onto the area element. So the unit vector of the area, just use n sigma there. So really, as we did for the volume case, we want to be able to relate an area and a path. And we trace the behavior of the electric field onto the path and relate that to the magnetic field threading through the closed area that path creates. And again, we take a limit. In the previous case, we looked at what happened under the limiting action of the volume collapsing down to nothing. In this case, we'll look at the action where the surface area collapses to nothing as well.
So, can you draw something?
Sorry.
Can you give an example of a draw?
Yep, we're going to do it right now. So.
You following this? You following it?
Okay, so again we have our boundary, and for argument's sake we can say we're moving from a material that's characterized by a permittivity of one kind and a permeability of another kind. And again, we can say that and likewise the permeability is quite distinct. So always keep that in mind as far as what we're talking about in this situation. So we've got a closed path integral. Now again, artificially I'm creating a very simple structure, a square loop. You could have a circular loop or some irregular loop, but it really doesn't matter. This just highlights the essential principles of the physics of the situation. We note here that we've got a closed path, and we take a certain circulation. So if we go around the loop in a certain fashion like that, and the length of our loop here is from there to there, delta S. It's just a path element. Because what we're going to do is, again, make this area. So here's our representative area d sigma. Again, remember it's a vector, and we can have this either facing out of the board or into the board. It just depends on what convention you want to use. And we've got the electric field doing whatever. But as the electric field interacts with this circuit, it generates a current, and the current loop generates a magnetic field that opposes the action of that electric field. So you have to imagine in here that you've got, you can check the direction of curl yourself later, but say if you've got the electric field, if you've got the current, for example, flowing in that direction, you put your thumb in the direction of the current, your fingers curl around the wire, and that's the direction of the B curl. So here you'd have the B lines going into the board and then coming back out inside the loop towards you. Okay? And the magnetic field it generates produces an opposed action to what the impressed electric field creates in the first place. So you've got a B field threading around inside that area. Now the limit, as I will put here, as that goes to 0, of first of all our closed loop term. I'll put the, should be consistent, I'll put the path element, and we've got ds. So we'll just look at the closed path loop first of all, and then we'll move on to the area consideration. Now, again, the whole emphasis is to see what happens either side of the boundary. The most obvious thing to do is to let this length collapse to 0, because that achieves for us making the area go to 0. You'll notice that the direction of the closed path operation takes us in this sense, going up as we cross out of this material into this material, but it's correspondingly opposed by a downward motion on this part of the closed loop cycle. So that any calculations you make on this arm as far as projecting the electric field into the direction of the current loop is going to be identically cancelled on this side of the loop. Yeah? So that all we have to worry about is what happens on this part of the loop in this material compared to what happens on this part of the loop in the other material. That's all it comes down to in the end. So that implies that we've got a tangential component of the field in one medium minus the tangential component in the other medium. And that's what we've got for one half of the situation. We need to find out now what happens in terms of the of the magnetic field. So again, we look at the limiting action as the area of the loop goes to 0 of what to you would be the obvious answer? We make the area go to 0 by just closing down the length of that rectangular area. So how much flux would thread through no area? Nothing. It's quite self-evident. So in the end, we can say that the tangential component from the contour integral between the two media is our change, but it's only looking at tangential components, and it equals 0. So we can say that in terms of the continuity of the electric field, the tangential components of the electric field are continuous across a boundary, which is quite different because we don't get a non-zero case as we had earlier, where the normal component of the displacement vector is actually equal to a non-zero quantity. It's actual area charge density. So if you want to stick that in words, you just say the tangent